Our next presentation is going to be by Amanda Terbeek. She's a GIS analyst at ESP Associates in Raleigh. Her specialties include floodplain mapping, flood risk analysis, and database management. Amanda has 5 years of GIS experience and graduated from NC State University with degrees in marine sciences and geology. Welcome, Amanda.
Thank you so much. So like she said, I work at ESP Associates. We are a multidisciplinary firm. We offer survey, planning, water resources engineering, which is a group that I work in conjunction with a lot, and I think earth and material science as well. I work in the Raleigh office, like I said, but we do have offices all over the US. And today I'm going to be going over a project that we worked on for the North Carolina Emergency Management. That was a flood analysis on the main stem portion of the Cape Fear River Basin. So the area that we're looking at, the Cape Fear River Basin, just some light geography, it spans about 190 miles. The headwaters start in Greensboro, North Carolina, and they let out right around where we are to the Cape Fear. Sorry, my notes are a little tiny here, but yeah, so the Cape Fear River is very often affected by flooding. I think we all remember Hurricane Florence was a major event for us. So it was a really important project for NCEM and for ESP. So here's just a summary of our project. We were to analyze multiple possible strategies for mitigation for the Cape Fear River and then complete a cost analysis for the communities based on those mitigation strategies and compare them to the baseline or existing conditions. So this project for the flood analysis kind of broken up into a series of tasks, and I just have a short description here. So we are to create our flood maps, which will have our water surface elevation, run our flood risk analysis, and then we are going to summarize our cost for the cost benefit as well as the impacts. So for our analysis, we are focusing on the Cape Fear main stem, which and we did not exceed downstream of the Cape Fear or the Northeast Cape Fear confluence. We were evaluating strategies that are just affecting along this area, and we were looking at our recurrence intervals from 5-year to 1,000-year. There are 8 total. Just some examples of mitigation strategies that were evaluated. We're looking at wet dam and dry dams, dike repairs, and channel cleaning. This is just an idea of where those strategies are distributed along our study area. An outline of our analysis, and this is kind of what I'll be going over today. We are extracting our water surface elevations from hydraulic models. We're creating our flood maps using that data. We're calculating our flood risk impact for buildings. We're going to aggregate those results. And then once we have those results, we'll be able to review our average annual losses. Sorry, I have a lot of animation, so I might be kind of married to this spot right here. So once we have a study area defined, there are some general steps that we're going to use to calculate our losses in flood risk analysis. So if we have our one study area, we can kind of break up our tasks into these broad categories where we're going to be running our mapping, our risk, and then we're going to summarize those results. So for our baseline conditions, where we have just one study area that we're looking at, baseline is just our existing conditions for the Cape Fear. We're able to just run through that process pretty easily, just going through those 3 steps. For mitigation scenarios, we have our study area split up into these 3 regions that we're evaluating. And then each region is going to have its own set of mitigation strategies that we're looking at. So it gets a little bit more complicated because not only are we looking at our baseline scenario, now we're going to look at scenarios for each region, which, as Doc would say, great Scott. Obviously, it was really important for us to be organized through this process. So we immediately went into how we're going to keep up with our file structure. We have all of our strategies organized, and then we also are sorting each task. So we're going to have our mapping in one area and our risk in one area, as well as our summary for everything. I love Model Builder. This is going to be a slight hype woman Model Builder presentation. So we use the toolbox that have models that create all of our necessary products. And each model will have a workflow already set in. So all we have to do is set the parameters. This way everything's streamlined and we can, I'll stop hiding the presentation. This way everything is streamlined and we can pretty much have anyone run through the workflow. Obviously we want our engineers and GIS analysts to review it, but it's a pretty heavy process, takes a lot of processing time. So we can split it along multiple machines from multiple employees, and then we can all look at it together. So one tool that we're going to go ahead and look into is just our Create 10 batch tool. You can see here we have all of our recurrence intervals, there's 8 of them. And then within each tool in the model builder, I just went ahead and set up the parameters so we can very easily plug in our custom, custom named data, but it's just going to have the generic name that's set up in the parameter. And then for our tint raster tool, same idea. I love the iteration features in Model Builder. I think they save so much time. And then this way we can name our output with a prefix. So then when the next tool needs something to find to bring into it, it has that prefix to use. So obviously I said, we're going to have multiple people working on this. We don't want them to have to go into Model Builder and open up opportunity to accidentally mess something up. So our parameters are just set up so you can easily plug in your workspace and have everything set out to there. There is some pre-processing before we can start this process. We have our cross sections that are brought in from the H&H models, and then our water surface elevations that are brought in as a table also from those models. We're just going to join them, and then that will be our input to create our tins. And then everything I'm about to show you is just the tools that we had set up in Model Builder. So our tins are going to create these 10-foot water surface elevation rasters, and they're just interpolating our cross sections to get that. I'll go back and clarify that our cross sections, they are densified to 200-foot intervals. So that's what we're using to interpolate across. We created our depth rasters. The depth rasters are the difference of our water surface elevation, our terrain taken from our water surface elevation. And then we're going to run an integer raster tool, and that is just going to take out all of our positive values from the previous raster, giving us a depth raster. So this is where we're seeing water in a flood event. And then we're going to run our raster to polygon tool, as well as a QC tool that just will clip each smaller recurrence interval polygon by its subsequent larger event. So our 10-year will be clipped by our 20-year and so yeah, I think our 10-year was clipped. No, 25-year. Anyways, and so next we're going to run our extraction tool. And so all this is doing is taking our floodplain polygons, and it's going to extract the polygon from the water surface elevation raster. So we have our defined floodplain. All of this gives us these products, which we're going to run through our risk analysis. So we have our polygons, and those are used to select the buildings in the floodplain for each event. And then we have our water surface elevation rasters. Those are going to be used to calculate our flood depth at our buildings. Obviously, a lot of QC is needed when we're doing this process. We're working with huge rasters. One way that we checked our elevations to make sure we were on the right track was by extracting elevations just at random points throughout the raster, and then checking the elevation value there to make sure it coincides with what we have for our cross-section values. One other way to just do a QC of our mitigation to make sure we're staying organized. This is just an example of a mitigation scenario, and we're zoomed into an area where we would expect to see changes. And we can see our baseline rasters, the red underneath the blue mitigation scenario. And our blue values, or I'm sorry, our red values are the baseline, and those are all higher than our mitigation, which is what we would expect for our basin to have a higher water surface elevation. For our, not here, for our risk analysis, our first step is to select buildings from each return period. And the building stock that we're using is actually from what John spoke about earlier. If you're in the previous presentation, they're just in NCEM's database. They have a spatial data download site where you can get these buildings. And then once we have our buildings, we can calculate the flood depth. And that's going to be the water surface elevation, or I'm sorry, the finished floor elevation, just the FFE subtracted from the water surface elevation. And then the next step is we're going to be able to calculate a damage or an impact cost or a damage cost, which will be split up by structural content and then other damages. Python, slithering in, being super helpful as always. This Python script is used to prepare our data to run through our risk geodatabase. So what it's going to do, it's going to create file geodatabases from schemas. It's going to load buildings from our North Carolina risk database into each event geodatabase. And then it's going to call this tool, and this tool is going to extract the water surface elevation at each building footprint. And again, model builder, come in clutch. It's going to interpolate the water surface elevation across the building footprint. And then we have a table that's going to populate our flood depth, which is just the finished floor elevation minus the water surface elevation. So once we go through our Python prep script, we have these products. And this is a geodatabase for each recurrence interval that we're running an analysis for. Our building footprints have the FFE and max cost values. They also have other attributes that are going to be helpful in summarizing our impacts. We have an empty table for costs that will be populated by the IRIS tool, maximum water surface elevation for each flood event, and the flood depth of the building. After these geodatabases are created, they're ready to run through NCEM's IRIS tool. So in ArcMap, the risk tool is accessible through ArcMap. We just have an extension for it. So once we have that opened up, we're going to plug in our geodatabase for the flood return period into our input. The output from this tool is going to be this table that has our damages populated for that building. So it's using the flood depth, the maximum replacement cost for the building, or for the contents or indirect damages. And it's going to grab a percentage of damage based on the flood value, apply that percentage to our maximum cost value, and then come up with a damage cost. And then we're going to run it through a Python post-processing script. And all this does is it's just going to take our values from all of these L damage results tables and put them into one large table that's going to have those values for all of our recurring events. To QC risk, we do a few different things. One of them is the top 10% damage evaluation. So we're looking at our top 10 values for our structural damage. And then we're also going to look at top 10 values for our building replacement costs. And just make sure there's nothing erroneous in there. Like if we have a $5 million gazebo, probably not accurate, unless it's a really nice gazebo. So one way that we like to QC risk is narrowing down an area of interest. So here I have subtracted the water surface elevation of our baseline scenario from our mitigated scenario. And then where I've subtracted the mitigated water surface elevation from the baseline elevation. And then I have an area where I can kind of hone in on where I'm expecting to see risk results. And these are the risk results that we're seeing. So we see, I have them color coded. So anything that's yellow is our baseline damages that are greater than our mitigated scenario damages, which is an expected outcome. And then also maybe our baseline damages are equal to our mitigated damages, and that could happen, and that's fine. What we would want to be interested in investigating is if we have a lot of situations where our mitigated scenario costs outweigh the baseline costs. And then all of this goes to our engineers, and they're going to evaluate our risk results and our rasters for another QC. Once we have our risk geodatabase populated, we want to be able to summarize our results by community and some other attributes I'll go over. So we're going to join them with the community boundary area. We're also going to join them with occupancy categories, and I'll kind of go into what that is. And then we're going to summarize those results so that they're all aggregated into this table that ideally will give us a breakdown of community impact for each flood event. Here's a look into this impact summary tool that we just put together in Model Builder. Our occupancy categories that we're bringing in, these are broken down into 3 general categories: residential, non-residential, and public. Residential, of course, you're saying your homes; non-residential, retail, and then public would be like our utilities or public works facilities. Once we have all of those attributes together, then we can go ahead and put together our impact summaries, which I went a little early there, sorry. We'll get to the joke. And so our output from the tool is this slightly more organized, but not completely ideal table where we can see that we have our political boundaries and our occupancy types as well as our costs, but it's still a lot to sort through. So
I hadn't drank very much, but it has cooled off. Okay. It'll help some. Thank you.
Gentle reminder to make sure your mics are on mute unless you have a real funny joke to tell.
Yeah, I'm not sure why that happened. Everybody's supposed to be muted, hard muted, and it's Zoom is unmuting.
That's okay. Thanks, Amy. So once we have our pivot table set up, our results can be output into this table that's ready to just go ahead and plug into our report. And this shows a breakdown of impacts by community. And we have one table per occurrence interval, per mitigation strategy, a lot of tables. So it's really helpful that we have a model builder tool that's just going to knock all these out for us, and we don't have to spend a lot of time putting them together. Our average annual losses are going to be calculated from those tables. It's pulling our damage costs and then applying an annual loss equation that I think we just use Whatson has this. If you want to go into that, I have a slide on it. And then this is also going to give us benefit costs. We're looking at the 30-year and 50-year benefit costs. And then once we have all of our average annual loss tables together, we can pull them into another table. And this one is going to be really helpful for us to evaluate our mitigation strategies side by side, so we can just see the annual losses, benefit costs all together. And we're also able to compare them to the baseline or existing condition. So through all of this, our final risk products are these 10-foot cell size water surface elevation rasters, these impact tables that we've created, and our average annual loss and benefit costs tables. And these are just going to be components of what go into an overall assessment of the flood risk, the flood mitigation study. There's also going to be implementation time and project costs, ecological studies. So this is just one small part of what we're going to be looking at going into an analysis. And this whole project, funded by NCEM, House Bill 200, it covers this mitigation strategy assessment. It also covers assessments for other basins, as well as the 2D project that Richard's going to go over next. So future steps, we really have a lot of room for automation here. I think we can go even further. Just trying to customize our output and also getting our results out of GIS into Excel without even doing any pivoting in Excel or anything like that. And also, I think John had a good point of having one project set up that can automatically plug in all of our environment data and then output our product automatically. That's all. I think I went a little fast, sorry, but now you can ask questions. Yeah. Mhm. Yeah. Mhm.
And Amanda, what was the question?
Yeah, so the question was if we have any communities that are outside of or that are unincorporated, how are we including them in our analysis? And yes, they'll get thrown if they're like an ETJ, I think it is. They'll be kind of brought into that community as well. We also did look at if we didn't have a community boundary, like a city or a town, then we instead were looking at the county as a whole, so it would be included in that. Anything else? All right. Cool. Well, if you do think of questions later, we have a booth outside to the left with some really cool lanterns. Sorry, I went too far. So feel free to come by and ask questions and get one.